challenge. Maybe I can introduce
Yeah, do you want to announce it? Yeah.
Yeah, since you are right.
Yeah. Okay.
Oh, it's green. You see menu.
Write down your name, sir, I already know this.
So, cool. I guess to start off, just to make sure everybody's got the links open, the main one you need is this one. And there's a QR code for it over here. As I'm going to try and paste it over here in the search so it's a bit more visible. But you will also see it in the email I sent out right before BiDS. If you just Google Dean or Dean Summers, you're probably going to see it there, the tutorial link. So just give everybody another minute for it. And maybe just to introduce myself, I'm Dean. I'm working for a small geospatial analytics company in Cambridge. And what we're working on is a lot with geospatial data analysis, machine learning, and a lot with open science data. One of the projects that we are working on is EarthCODE. And it's one of the big initiatives from ESA for open science, for implementing their open science strategy. So today what we're going to talk about is EarthCODE, how you can get the data, how you can use the data, how you can engage with the project overall. If you're working on any relevant projects, how you can publish your data and make it open and available for everybody else. And then also we're going to introduce PanGeo, which I'm quite sure a lot of you will already have heard of or have been a session for. So we're going to introduce the platform, talk about the deployment we have on EarthCODE for PanGeo, the PanGeo stack, and how you can use that. And then we'll go into an introduction and tutorial for using it with some of the data that's available in EarthCODE. So just to get a feel of the room and get an idea about what background people are so we can move along quicker on some parts of the workshop and focus on others. Who's coming here as basically a full-on data science background who hasn't done GIS before? Okay, we got one person. That's great. Good room. Who's already used Xarray, Dask, Pangeo, has heard of the general stack, knows about how they work, knows the libraries? Okay. Who is doing Python, just knows Python well and is working on the Python ecosystem? Okay, the rest of the people, are you working on sort of R, MATLAB, that sort of an environment, QGIS, ArcGIS? You're doing the geospatial background. Anybody want to share what sort of tools they're using to work with the data, Earth observation? Okay, how about who's doing any sponsored work from ESA, who's working on a project that's sponsored by the European Space Agency and is producing data or algorithms? Anybody? Ola? Yeah? Great, we've got one or two people. Okay, great. So, and last one that I didn't get a show of hands for, so we know whether to skip or continue on that section. Who knows Xarray? Okay, so we're going to go through that as well. Great. And has everybody had a chance to open this link up now? Who hasn't opened up the link? Okay, I'm assuming everybody's got it now. Perfect. So, first things first is we'll start off with introducing what EarthCODE is and talk a bit about this session. While I'm talking about EarthCODE though, there's a cloud environment you guys can set up in the background. If you go to setup, so we can handle it off here so we don't have to do it in the middle of the workshop. If you go to introduction and then setup, you should see a running on EDC EOX Hub workspace, which I'll get into in a bit more detail in a bit. But if you click on this link over here, it will take you to this sort of a web page. It won't look like this because you haven't been approved yet for the workspace, but it will send me an email so I can approve everybody in the background for it. So if you can just go there and click on this, I'll have a request on my end and I can start accepting people into the workshop. I can see quite a lot of people already have clicked on it. So I'll start accepting. Okay, so in the background, if you can just go again, introduction, setup, and over here to this workspace link, I'll be able to accept you and give you access to the cloud environment for running all the notebooks, examples, and everything else. And I'll just very quickly click. Actually, Ola, could you come by and just help out with clicking on the accept links? Yep. So I can cheers. Yeah, and if somebody has a problem with the environment or something isn't loading correctly, just let me know, let me or Ola know, and we'll come by and help. Okay, cool. So, first things first, let's introduce EarthCODE and talk a bit more about the project. So, try to zoom in first. There we go. So, as part of ESA's 2024 strategy, open science is front and center. And how they define open science is via 8 key sort of pillars. Starting from open data, open source code, linking that code to the data to make sure that it's reproducible, knowing what experiments were produced, using which input data, output data, and then what code, and then making sure everything is open access, including the documentation papers, and the whole environment around that as well. The other key theme is also putting in open platforms that can run the code that produce the data so as to make reproducibility an actionable step. And then to have a community engagement all around this where there's open resources, educational resources, there's a community environment where people can comment, work together. Basically, there's like a very much community-driven engagement towards getting the open source and open science community involved into the process rather than just doing open science for the sake of it. So what EarthCODE is, it's one of those implementation, and essentially at the core of it, the idea is that it implements the open and fair principles in one platform. So beyond just an acronym, FAIR, what it means is making data machine readable and machine accessible and machine actionable. With just data being open, it's not really enough for action to happen, really, for Earth action to happen. The difference is, so open means literally the data is open, accessible, and so on. Fair means it's quality data and it's described well. The two together essentially support each other and build an ecosystem where you're able to publish and use the data in a very sort of actionable way. As in, think of an example. I might have fair open data in a PDF file with, let's say, crystal structures as the typical example they use in the FAIR community, where like some chemistry papers published their PDF file with all the data, with all the images of the different crystal structures, but it's like a 900 PDF page file, which is very hard to access, use, and so on. So that's a very bad example, but the good example is, imagine you have metadata that describes your data. You have essentially a way to directly via API open up each individual variable of your data, explore it, it's well documented, you know what the data is about, you know what units it's using, it's combined directly with libraries that would use it. Let's say in the field of Earth observation, you can use something like QGIS directly to load it, so on and so forth. It's well described. Let's say if it's Earth observation data projections, resolutions by default, and you don't have to do any of the guesswork yourself. That's the idea, making the data much more actionable and directly interoperable findable and interoperable between the whole wide ecosystem of data. So EarthCODE tries to combine basically these two concepts, making data open and making data fair, and providing the ecosystem and infrastructure for that with reproducible platforms. Essentially what that looks like is it bundles up data, workflows, documentation, papers, and publishes them on something called the Open Science Catalog, where they're accessible and reusable. It has something of a concept for platforms, where you're able to essentially use the code that was published to reproduce the results and reuse the code itself, or develop initially the algorithms for what you're trying to do. And then essentially maximizes the visibility of the science outputs and tries to make them a first-class citizen when it comes to research outputs. So how this gap is what's the gap to getting there essentially, and what EarthCODE essentially provides is three things. There's a need basically for this to happen, for the piece of vision to happen. There's a need for access and process of satellite and in-situ data in collaborative environments. There's a need to develop and publish reusable code and workflows. There's a need to validate the outputs and show reproducible results, and a need to collaborate across institutional and national boundaries. Essentially what the fair and open science infrastructure we need, which EarthCODE tries to provide, does is it provides a way to essentially, using the fair principles and open science principles, have data published somewhere where essentially it's on the web, it's accessible via open tooling, open platforms, and so on. That data is described in interoperable formats and with rich metadata. So that data sits somewhere on the web, it's described in metadata, I can call it with an API, it's machine readable. The other aspect is the workflows that produce that data. So I have access to workflows that essentially, that's the code, that's the environments, that's maybe a containerized sort of environment where I can run the code, like a Docker container or something like that, something that's portable. And essentially, there's a concept of that that's deployed somewhere which is connected to the produced data. And finally, there's like the platform that is used to run the workflow that produced the data, and that's also openly described via rich metadata and published and available. So the idea is basically to provide this sort of a fair open science ecosystem to make the data, to make the code machine readable, machine actionable directly. And how EarthCODE essentially does that is via three sort of key, I would say, features. So first of all, everything's accessible via the EarthCODE portal. So if you go to earthcode.esa.int, which we have a link to in the tutorial page, you'll be able to see all the different aspects, but everything, the whole ecosystem is accessible via the portal. there is something called the Open Science Catalog, which is essentially a stack catalog. Can I have a raise of hands of who knows stack? There we go, about half the room. So essentially, it's metadata that describes the data, and it's a browser, stack browser deployment. So essentially, you're able to go through and see what's openly available and access it. There is a concept of integrated platforms, and that's essentially, if you look at the chart over here, that's the compute that you can use to reproduce and create workflows to produce the data. There's several platforms that are integrated so far in EarthCODE, and there's more upcoming as well. So it's a continuous process to enrich and develop the ecosystem. One of the platforms we're going to use today is one of those integrated platforms. It's Pangeo on the Euro Data Cube, and we'll get to what it does in a bit more detail in a second. Okay, so the Open Science Data Catalog, that's essentially just a catalog for metadata. The actual data is typically held on the ESA storage repository, and that's where it's basically like a long-term storage repository provided from ESA. So if you are running an ESA-sponsored projects, you'd be able to upload your data, your results over here, and make them available to the world, and ESA would manage that for you. Now, all of this is connected via a forum as well, where you're able to basically access whatever people are saying about the different assets that are deployed, speak with the community, engage with the community in different ways. Okay, so who is this essentially for, and how people tend to use it is in different ways. So there's three sort of key groups of people that we engage with typically. The first one is ESA-funded research projects, and that's anybody who's working on ESA-funded research or EC member state-funded research. Essentially, there you would be able to publish your work directly to the Open Science Catalog. You would be able to use the platforms, reuse the workflows that are already existing that somebody else has deployed, and so on. The larger community, I'd say, is like the community of users of that open data, which is the scientists and developers in general. And the idea there is for that community, they can search through, they can use the data that's deployed for their projects, for their work. They can contribute new tools and workflows and engage with the community, essentially, so that the scientists from ESA and the whole open source community can use their tools and workflows that they've provided in both. And finally, platform providers, essentially, they are the compute, they're like the data access sort of part of the ecosystem, and they provide the integrated platform experience for EarthCODE. They form essentially that environment for development. So first of all, we're going to explore essentially how this workshop breaks down is, first of all, we're going to explore the Open Science Catalog, then we're going to explore visualizing some of the data, and then we're going to use that data directly in Python and the Pangeo ecosystem. So as I said, the Open Science Data Catalog is essentially a stack catalog. And I think it best would be to just open this link and start exploring that together. So it's at opensciencedata.esa.int, or you can scan this QR code. And I'll open it up over here. So I'll just give everybody a second to open it up first. Cool. I'll just go to it myself. Has everybody had a chance to open it? Anybody want to see the QR code again? Okay.
Registered on the site?
I think so. Do you mind coming in and just accepting them, Ola? Just clicking the accept link over here. Cheers. Good. Yeah, just basically click through. Like so.
Oh, you just like it.
Yeah, literally just clicking it. Okay, so the Open Science Catalog, what is it? It's essentially a catalog of publicly available geosciences products that were developed by ESA scientists, and this is where they're stored, by ESA-funded projects rather. So what does that look like? First, starting off from just, let's maybe take one example and start off from the smallest sort of step. So, and I'll leave you a couple of minutes to explore it yourselves, but just to guide you through it first. So essentially, if we look at it, it's what is a stack item? It's essentially just JSON metadata. We're going to stack how it's organized and so on in a bit, but essentially, as far as you're concerned, it's just JSONs that are getting visualized somehow, and there's some sort of an ontology behind it that puts some meaning behind the different metadata that gets described here, so that essentially libraries can then pick it up and make use of it, like Python libraries and so on. So what does an asset have typically that's published to EarthCODE? It has a description. So let's say this is a ceasefire cube. What we're looking at here is a data cube that has multiple variables describing essentially different aspects and features you'd be interested in when you're trying to model wildfires. Things like air temperature, things like how much leaf area index, things like how many burned areas there were on a particular place. And what this was produced was part of a machine learning project that combined different data sets to build this data cube, essentially, with the different variables. So there's a description. There's some keywords that describe what the project is about. There's a license that's attached to it. There's a temporal extent of what dates the data reaches. So we can see it's from 2001 to 2021. There's some metadata about when it was created, by who it was created. There's a CF parameter, which is the standard CF name of what it's trying to model and what it's trying to describe. There's essentially some links to the Open Science Catalog variables. So variables is essentially something we use to describe from internally the Open Science Catalog what variables the data describes. So essentially then it has something like, it has a DOI directly that points to the metadata and the data itself. It has different themes attached to it. And why is this important is because you can basically use all of this information to find the data. So if, for example, I'm looking for, let's say, themes under land, I would be able to explore all the products that are similar to this one and are about land use and are deployed over here from the Open Science Catalog. So it gives us that rich sort of plurality of terms to search through so that we're able to find the correct data we're looking at for, essentially covering the findability of FAIR. So that's one thing. There's metadata, but there's also data. And the data is, in this case, it's a ZAR data cube with many different variables with descriptions over here. So this directly opens up the data for us. And essentially, you would be able to access it directly by just copying the URL, which we will do in a second, copying the URL and opening it directly, or programmatically accessing the stack catalog and trying to find it like so. So okay, that's the sort of bottommost level of products that you would see. There's also a topmost level, which is the catalog itself, and there you're able to browse through the different products in different ways. Like for example, I would be able to go through and based on the EU mission, so the tools that were used to collect the data, initially the instruments that were used, I'll be able to filter through like so to find different products. I would be able to use the variables directly. So if I'm interested in, let's say, modeling a particular variable, I would be able to search for it like so directly. So let's say burnt area, I'm interested in forestry again, and we can see the ceasefire data again. So there's all sorts of different ways you can use to access the data and get to it. What there is also is a direct search, which you would be able to use to, for example, if you're interested in a particular region, let's say I am interested in somewhere in Eastern Europe. Let's say I'm interested in crops, and it will give me a free text search over what exists in that region. Let's say land. So essentially, this rich plurality of terms and data and metadata gives us different ways we can find and access the data we're looking for. We're going to get into how to actually use this data in a second, but this should give you an idea about what the Open Science Catalog is trying to do. Underneath, again, everything is basically modeled into a GitHub repository, which you can access. It's openly available over here, and you can use for your own purposes. It's all modeled as stack data, as a stack catalog with stack metadata and items and collections attached to it, which you can go directly and browse. And how contributing to this open science catalog works is basically you pull the repository and you commit a JSON file to it, essentially, to keep it simple. And then upload the data, make it accessible, and so on. So what I would suggest now is maybe have 10, 15 minutes to just explore the open science catalog, find products you're interested in maybe, or just explore it in general. What we'll do next is go through actually accessing it programmatically and visualizing some of the data. But now let's maybe give till 1:15 or 1:10 to just explore the catalog. And if you have any questions, just raise a hand, and Ola or I or Annie will be with you.
People have access to the Jupyter Hub now. Anyone still issues with that before? I didn't think about 5 messages.
Yeah.
Shout out if there's something.
Yeah, does everybody have access to the Jupyter Hub? Well, who doesn't have access to the Jupyter Hub is the question. Okay, everybody seems to do. If you don't or you have any problems, just raise a hand and we'll be with you. Let's give everybody 10 minutes in the meantime. Can you try and refresh if you're Yeah? Oh, you just sent a request. Okay. Okay, cool. I'm just gonna accept you. Try and refresh. Great. Cool. And we have another 5 minutes to just explore. I guess in the meantime, does anybody want to share what they would like to, before we get into the actual Jupyter encoding side of things, does anybody want to share what they want to get most out of the workshop to just have a focus area? Hold on.
I mean, I'd like to learn more about that, to access, just generally access calculating. I'm not a good example user of SAS calculator, but
Okay, so accessing the data is one thing.
yeah, I want a boring answer.
Yeah,
Think
no.
more about it.
No, that's a good one. Yeah?
Sorry, I don't know how topical it is for the whole session topic itself. But what I see from the product search now is that are there any geographical imbalances between the data accessibility? Because now, for example, when I was trying to look for search results within the filter geometry, let's say for Northern Africa, I got basically like 0 searches. I started like country specific, and then I was like, okay, for Morocco I had 0, and then I was like, okay, maybe I'll check, whole North Africa. It was 0, and I had a similar kind of limitation for Middle East, like MENA in general. So
There aren't any. I think it's more like the search probably has a back-end problem because there's a lot of global data. Like, for example, the fire monitoring data is global variables for, let's say, mean area temperature for places. So I think it's probably the intersection is confusing it with a B box, and it's only giving you data that's within that.
yeah, because when I put like the intersect filter geometry, like that takes a bit broader, I guess.
But there aren't any like conscious decisions for or like products we're not accepting for that. I think most are actually targeted at a global scale, and there's a variety of different. Like for example, every project I think is focused more on. I would say like the majority of projects are focused globally, and a lot of them are focused like on random, different geographies, countries, and so on. So there's no focus around that. But thanks for the feedback. Oh, actually, that's interesting. Stuff does actually show up when I search in Africa. Let me come by and see if there's anything. Might have set up a filter or something.
Yeah, because I didn't.
share any interesting asset or data they found so far from the Open Science Catalog. Yeah?
Just a clarification. This catalog, let's say the output of the stack items is the collection item, and there are also nested items under the standard side.
So for the catalog here, for the Open Science Data Catalog, it's catalogs, and all of these are different catalogs over here as well. So it's a catalog and a catalog, and then the data, the products, is a collection. And then within that collection, typically, you will either see an access link. This is like as a stack data link, and that's one way to access it. Or there will be a child collection, or a linked collection rather. A link as a child collection is the right term. And that collection will then have the data as an item. We'll have a collection that has a stack item that has an href and an asset in it with the actual data.
This works with the stack API.
Yeah, I'm going to actually show it in a second. Cool. Okay. I'm going to go into exploring the data now a bit more. Feel free to browse in the background while you're going through the rest of the session as well. But one of the things that EarthCODE offers, and one of the things that the EarthCODE platforms offer, are these platforms. And these platforms aren't only for developing code, they're also for visualizing it and essentially showing the data in some way, shape, or form that makes it more usable, more accessible for, let's say, if you want to communicate with policy, if you want to publish your project somewhere, if you want to make it more visible. There's tools for that from the platforms. One of the tools and the ecosystems that EarthCODE contributes and works with is the EarthCODE ecosystem. And if you Google EarthCODE viewer, there's also a link in the workshop, but this would be an easier way. If you click on DPSDL EarthCODE viewer. So EarthCODE viewer is one of those libraries that essentially visualizes the data. This is a deployment of EarthCODE viewer from DPSDL. And what you can do with it is visualize data cubes. Now, who knows what a data cube is, first of all? Does anybody know what a data cube is? Okay, maybe just to give a 101 on that. Data cubes are essentially multi-variable, multi-dimensional data sets. The typical thing you would see in a data cube is you would have multiple dimensions like x, latitude, longitude, and time. And then you would have different variables on those dimensions that are aligned together on the same grid, on the same projection, and you're able to access them essentially in a much easier way. So it's like a 3 or 4 dimensional or however many dimension structure that you can then access in a common way for getting variables about typically Earth observation, but anything else for that matter. So for all intents and purposes, this is the data cube that we're going to be exploring, ceasefire, and what we'll be able to see in EarthCODE viewer, what it allows us to do is visualize all the data from it. What we can see is the different variables that this data set has. And by the way, this data set is the same one I was just showing earlier over here in products. If we go over here, if we do ceasefire, same one over here. This is the data that I'm showing. And if you go to EarthCODE viewer, you would be able to click on ceasefire cube. It's loaded to be visualized there. There's many other tools in the EarthCODE ecosystem for visualizing data as well, but for this one, I think this is the best one to show it. And you can see all the different variables that are sort of displayed here. So for example, leaf area index, there's, let's say, areas for burnt, let's say burnt areas, and this is like basically statistically, this is the official data from GWIS about what areas were burned and how many acres of that area were burned at certain times. I think it's loading a little bit. There we go. So you would be able to see here, for example, there was a burned area at this point. What you can do with it is also do some preliminary sort of analysis to get an idea about how data is changing and what's going on with the data. Let's say if we select and draw a polygon over Europe, we'll be able to, whoops. There we go, loaded data. We'll be able to see some of the data that gets loaded. And as we can see, which is expected, there's some seasonality over leaf area index, so how many leaves depends on the season. We can also see, we can also get some statistics of the data directly just to give us an idea about what's in there. And we can look through the different variables. So essentially, this gives us a bit of an idea about exploring the data before we actually start diving deep into it. Now, one thing that we'll do is essentially go and select an area of interest from here. So I've already selected one in a notebook over here, which I'll show in a second. But if we would like to just view or analyze an area in particular that you're interested in and see if there were any forest fire during the time, what you can do is just go over into the draw polygons, pick the area of interest. For example, I've taken a look at Portugal over here, and I'll just draw my polygon. And then what you're able to do is export a GeoJSON that describes that polygon directly from here. So if you click on the download at the top right and you leave in this include places GeoJSON, you'll be able to download it and get it then to use it for other things. So, which we'll get into a second about how we're going to use that. But basically, this allows us to visualize the data. You can access, there's a bunch of other features as well, like for example, overlays and changing the base maps and customizing the visualization. Also, this is like an open source library. This is a website that's basically an open source library for visualizing data, so you can load everything and display everything in a notebook as well using Xcube Viewer, which we have in another workshop. But besides the point, if anybody wants to analyze a particular area that they're interested in and just see forest fires there and what's happened, select it over here, and then download the GeoJSON through here. Okay, so now we're going to get into the actual environment and start hacking away. So you have already seen the Open Science catalog, and you can, if you go back to it and you click on catalog, there's something else I didn't mention last time. And if you remember, like on the presentation, I showed the idea of having workflows, reproducible platforms, and stuff like that in the ecosystem. And that's also published and modeled in the Open Science catalog. So if you go into workflows, and this is a fairly new deployment on EarthCODE, but if you go into workflows, you'll be able to see the different code that people have deployed and made accessible for the data products they've produced. We will today explore this workshop training wildfires workflow. So if you go to workflows at the bottom, and then you go into workshop training wildfires workflow, you'll see some information about the workflow. So what can we see here? There's some description about what it does, demonstrating how to fetch Sentinel-2 data and generate burn severity maps. It talks about like the application and that it's running on, which is a Jupyter notebook in this case. Some information about the kernel that it's using, which is the environment basically, the Conda environment in this case. Has some information about the platform, which is Pangeo in this case, and the typical themes and project sort of associations you would see. Now, it also has a GitHub repository where you can access directly the data, the code itself. But more importantly, and why we were logging into the environment just an hour ago, was because there's this open notebook on the EDC platform button. And if we open this, what this will do, and by the way, when you create this environment, you'll be taken over to this screen. Make sure to select 4 GB of RAM and 2 CPUs because your memory will crash if you try and do it with less. So just make sure you select the biggest machine you see there. And you start it. It will start essentially a Jupyter instance into this EOX Hub environment. And you'll be able to like start using the workflow. Now, this will clone essentially this GitHub repository, load the kernel and the environment there, and let you run the notebooks and start using them. So this should run and clone the environment. You should see, essentially, you should be taken over. Yeah, there we go. Should be taken to this Pangeo and EarthCODE notebook. Now, we won't start from this one. We will start essentially from, if you go back and you go into EarthCODE 101, we'll first access data we were just looking at programmatically via the Stack API and talk a bit about Stack. And then we'll get into the Pangeo ecosystem and more general. Okay, so just to again go through how to access this, if you go on Catalog, go on Workflows, there's a workflow for workshop training wildfires workflow. And if you scroll down, there will be open a notebook on the EDC platform. And you should be taken over here to this, Pangeo EarthCODE notebook. Go back one step into EarthCODE 101 and open this Stack and Data Access notebook. So I'll give everybody just a moment to get there. And if anybody needs help, just raise a hand. Just walk around to make sure everybody's got it.
It was the wildfire?
Wildfires one, yeah. Yeah.
I had some trouble with the server starting. So I arrived at the point, but when I try to... First thing first, there is no the other...
Were you at the Yodash tutorial earlier?
Yeah, there is no the other list, but I
Right.
follow all the...
Try and log out.
I don't know, probably it's stuck in the previous session.
Yes. It's exactly that. We've seen that a couple of times. Sign in and out again. I'm going to ask the person who's managing it in the background to remove your thing from there so you can continue on this one. Can you send me a GitHub handle or anything so I can just pass it on to him?
Okay, the GitHub name is this one.
Okay, I'm going to just take my laptop so I can send him a request.
No, the problem is the first row in the image.
Yeah.
You should have another option in drop-down list. My name is Barry.
Okay. I'm just going to send a request over here.
Yes.
Yeah, so.
Yeah, for sure.
Having the same problem. So I don't know if this is a research program.
Please go ahead. I'm just chatting with the person who saw the error.
No.
So that's perfect timing. Vari.
A-L-E.
17.
17. The V is capital V. I don't know if it's different or not. Here is in lowercase, but on GitHub is uppercase. I don't know if it's matters or
Yeah,
not.
I'll just paste that.
It's an extra info.
Yeah.
I think that
So we have
she has
few
the same
people.
trouble. And
You have the same issue with Yodash. Okay, so they're going to refresh that now.
Stuck in a previous session. So the first row is the name of the session you were in previously.
Yes.
Okay, so they're refreshing that one, and just follow, I would suggest, on the screen over here. I'm going to go through everything, and then basically in the background, they're going to reset the cookie and everything else so you're able to log in with the right one. And if you have an option, select the EDC Pangeo profile instead of the Yodash one. But they're going to reset that now. Okay, cool. So just continuing on here, and just follow along, and then I'll let you know when it's ready and done on this side. So this environment. Has everybody else managed to open up the Stack and Data Access notebook? Again, it's in BiD tutorial, and then EarthCODE 101, and then this one.
I don't see this BiDS'25 tutorial folder.
Ah.
On my side it just says it's shared.
Let me just take a look. Can you go to the Open Science catalog?
What is this? Where did
It's
you-
not cloned, the repo.
Yeah.
Can you go to the workflows in the Open Science
I can,
catalog?
I can-
Yeah, okay.
Yeah, That's not the right one.
And the ceasefire. Oh well.
I need to go to a specific.
Yes,
Yeah, 'cause
because
what it-
that's an example where. So it
What it's going to do is essentially clone the repository for the workflow that you're trying to access. Okay.
Okay, stop.
Too many tabs open. All right. Anybody else having trouble getting here? Yeah? Come on.
I'm unable to start.
So wrong one. I think you were also at the Yodash tutorial,
Yeah,
right?
sure.
So
Okay,
if you
so
go
it's-
back a step,
Where do you want me to go?
can you go back and like try and open it up again? So,
Simple refresh.
and log out.
Ah, okay, fair.
And log in with your GitHub. There we go.
EarthCODE.
Yeah, this one. EOX Jupyter Lab. Yeah.
Yes, I have run.
Oh, okay, we have everything else. So
We are set up.
all set up.
Yeah.
Hey, there we go. Ideal. Okay, so I think most of us got here. If you have any trouble, just Annie will come and help out in the meantime. So this notebook, Stack and Data, just start with the imports first. Let's maybe quickly walk through and see what we're doing. Okay, so you downloaded a GeoJSON just now from here to explore what area you're looking at. If you want to explore your area of interest, you can go to this AOI folder and just replace this feature GeoJSON with your feature. So just paste it in here, just you can drag it and you can drop it over here and just change the name of this user polygon to, well, delete this one first, and then rename it to feature.geojson if you want to explore that. I'll stick with the example we have already. So, okay, what are we doing first? We will essentially just visualize using GeoPandas the polygon that we're trying to look at. So GeoPandas, has everybody heard of GeoPandas? It's okay, I think most people are nodding their heads, so great. We're just loading the polygon here to show the area of interest that we're going to try and get and find. So we are essentially, if you saw this website bit where we're trying to search through products, essentially we'll do this programmatically now directly via Stack and Stack APIs. So okay, just a refresher, Stack, what it is, what the whole idea is. Essentially the vision of Stack is to create a sort of web network of spatial temporal data and assets, things like satellite images, things like remote sensing data, and so on, and describe them in a sort of common language so that you're able to find them throughout and discover assets when you need them for your work. So the idea is to improve that discoverability, and essentially it's like a hyperlinked sort of internet for spatial temporal assets, where you have metadata of Stack catalogs, which are essentially, you can think about them as websites, and then those are connected in a web between other Stack items, which might be catalogs, items, which might be like assets, which might be data, and essentially it gives you that ecosystem where you're able to search through them via the metadata they provide, and then you're able to directly access them somehow via, again, the metadata they have in the Stack item descriptions. So the way you can think about it is essentially it's a folder structure with files as the data. And Stack as a folder structure just gives you a way of making your data, first of all, findable in the first place, where you're able to go to a folder, find a folder in the first place, search for the folder, and then you're able to collect the folder and separate it out in a way that it's well organized. To explain how that works is essentially have three key features in Stack. You have three key classes, if you want to think about it like that. You have a Stack item, and the Stack item is like the bottom level, most item you would see. And what it is in a nutshell, it's just GeoJSON that follows a certain specification. And that specification tells you that you need to have some ID, you need to have some stack version that you need to have a description, you need to have something called links, a title, and the stack extensions you're using. Well, sorry, that's a collection. The item is the license, the extent, the providers, the keywords, and so on. So what essentially, okay, sorry, no, this is the item. So essentially, the item is like the bottommost folder that you would see. It doesn't contain the actual files, the data. It just is a descriptor of the data that you would use. So essentially, what you would have is something that has a link to the data, and then you have the bounding box of that data. You would have some properties of that data. Like, let's say if you're looking at satellite image, you would have something like how much clouds there are in that image. There might be some other properties, like let's say variables you're trying to model, like we have in the ceasefire cube. So if we look at, for example, over here, and I'll actually have it open. So over here, these variables are directly taken from the stack metadata. And if I just look at the stack item, I would be able to see things like essentially the time. You can't see it in the metadata here, but there's basically some bounding box of the area that it covers. And then there's a link to the actual data. And if I go and open this up directly as a JSON, might be a bit of an ask, but OK, let's just continue. So essentially, it's just JSON metadata. And what it does, it provides you that information that you can then use to query the data further. The collection is a top structure, which has many items or catalogs. So a collection, essentially, the difference between a collection and a catalog, it's the folder. The only difference between a collection and a catalog is that any item that's within a collection inherits the properties that the collection has. And why that's important is because let's say you have a license, think about it this, you have a folder, and you have some metadata about the license of anything that's under that folder. What's going to happen is the stack items under that collection, they're going to have or be assumed to have the same license as the metadata in the folder. So a collection essentially has metadata as well. It has the fields for extents, providers, keywords, assets, summaries of the data. So for example, you might have, let's say, several satellite images in a same collection. You can basically grab some averages, some, let's say, statistics, and expose them in the metadata directly. And why you would do something like that is essentially, let's think about cloud cover again, because it's a good example. If you're looking for cloudless images that you can analyze directly, you would be able to filter those on the collection level and only analyze the stack items and the stack assets that are quality enough for your research to be done. So that's collections. And then catalogs, essentially they have some metadata as well, but essentially the idea behind a catalog is that they have links to the collections that hold the stack items that then point to the actual data. So stack also comes into, so the way you can expose sort of your stack items is in two different ways. You can either have a static stack collection, and that means basically you just have stack files. And the open science data repository is just that. So if I just open it up over here, actually on GitHub here would be easier. It's essentially a bunch of JSON stack items that you see here as files. And that's one way you can essentially expose stack data. And if I click through everything, if you just go yourself and explore the GitHub repository, you'll see everything is basically just JSONs and JSON files. So there's that way of exposing it, and then you can expose it via an API. So let's first just explore it as a static catalog and see what you can do there. So how it works is you have different libraries that can help you explore stack. So you don't have to crawl through the, let's say, so you don't have to interpret this yourself and write all the code, boilerplate code yourself. There's a library called PyStack which essentially helps you out with exploring catalogs. What you can do with it is you can give it a file, a catalog file, and what it's going to do is crawl that file, and it's going to essentially interpret it itself, and then you'll have the functionality of Stack within it. So what it's doing here is we're feeding it directly this file that contains all the links in the Open Sans catalog. And what the Open Sans catalog is, again, is essentially a catalog with many different catalogs with many different collections between those catalogs linked together. So if we look at it over here, this is another view. If you load it up, you'll see the catalog over here. Topmost collections. What we can see here in the links is that there are different child links that have essentially different catalogs, again, for variables, for themes, for projects, and this is essentially different ways we're linking to the underlying collections data that actually have the data references directly. So programmatically, you can access things like the title, descriptions, all the properties you see over here. You can search through the catalog, you can get children. This is how you can go through the catalog. Let's say if you want to get one of the child catalogs, there's a function called getChild, and you just have to send it a ID of the link that you're trying to get. So let's say over here, the ID of, there's a product somewhere in the links. There we go. So you just pass it the ID of it, and you're able to get the catalog. So you're able to search through it, and we'll get into why we're doing it like so. So basically here I'm just building up a small Lambda function that essentially looks through all the children collections that are under this catalog. We can see there's 300 items. So what it does essentially, it's looking through all the children, and it's trying to find some search query that I've described, and it's trying to match anything that has the search query in it. And then it returns the Stack collections that have that query in it. Okay, what this is going to do then is, let's say we can search for a term, and that term is fire. If we just run it, it's going to take a second, because what it's doing, it's going to crawl everything and basically do a search for us. So as soon as it loads, it's going to give us a collection ID for the ceasefire cube, and this is pretty much the same as us doing a search over here for fire. An Open Science catalog. And then what we're able to do then is directly get that ID, get the item that has this ID via, again, getChild. So essentially what you're doing is you're crawling through the folder structure. You're going through folders for folder to get to a certain item you're looking for. And this, again, will interpret, if you do it like so, it will directly interpret this as a Stack collection, and you'll be able to crawl through it again and explore it using the PyStack library. Okay, and as we can see, this has the metadata attached to it. It's the same thing we saw in the browser, but directly now we're looking at just the JSON metadata. So it has the keywords we were looking at. It has some temporal and spatial extent of what the data has coverage for. Has links to variables, missions, themes, and so on. Again, this is just basically JSON data. Then what we're able to do is, from this data, we can explore it over here. And if we just go through the links that it has, we can see that there is a child link, which is another catalog. So what we will do next is access that catalog and crawl through and search through it. And here, this data, now, as we can see also, it's hosted somewhere else. It's not hosted on GitHub. It's not hosted anywhere like that. It's hosted on S3 bucket somewhere. So this is the user's data, essentially. This is where like the Open Sans catalog ends, and this is where like user basically has the opportunity to define the data using community best practices. So it's like accessible via common APIs like Stack and so on. So that's why it's hosted elsewhere, next to the actual data itself.
Sorry, may I ask a question?
Yeah, go for it.
How do you guarantee long-term access to this data if it is external?
So this is external from the Open Sans catalog, but it's still managed by ESA and the data stewardship team from the EarthCODE. So by external, I meant external to this GitHub repository, because basically Stack, you don't need it You actually asked a good question, because Stack, you don't need it to be on the same server, you don't need it to be in the same space, it only uses hyperlinks. So this S3 storage bucket over here that you see, that we're grabbing, somewhere over here, yeah, is a Cloudflare storage bucket that's managed by EarthCODE and the EarthCODE team. So the Stack item is uploaded there and managed by EarthCODE again. And basically users make submissions to EarthCODE that get manually checked and reviewed by the EarthCODE team, and then they get deployed into the Open Science Catalog. And typically the items and the data will be managed either on the project's repository or other repositories that are sort of accessible to the EarthCODE team, if that makes sense.
Repositories by definition are not persistent, so actually I still don't understand how you can guarantee persistence, because that's the requirement for fair principles, needs to be persistent. So this data can be changed, so how do you guarantee that it doesn't change?
Well, what do you mean it can't? That's the thing, we version it, and we monitor it, and we maintain it ourselves.
It doesn't have a persistent identity.
It does have a persistence identifier as well.
Because this is not a research data repository like Zenodo or Picture where we seal the data. So this data is not sealed, right?
Well, it is sealed, this one. This is not a persistent archive of ESA.
No, this is again one of the archives that ESA has. So if we look at over here, this, just to find the asset, it will have an PID to it.
At the moment we don't, you don't mean that we don't have the DOIs, but we will. Yeah.
Well,
We don't have yet the persistence. Yeah, I mean they don't mint the DOI yet.
so
But the data will still be there. So the data is persistent there because they will not remove it, but they haven't put in place minting of the DOI.
yes, and if we look
So
at
once you mint the DOI, it's guaranteed. I mean, they should use the persistent identifier.
yeah.
Yes, you are definitely right. At the moment, it is not. It is persistent, but it is not using a persistent identifier to identify persistently
Right.
the data. You are telling me.
There is a DOI attached to the data as well for a different version of the data, which is over here as well in Zenodo for now. But we're moving basically all of that to EarthCODE as well. So
But the data and the metadata is really important to have a persistent identifier.
right.
I think that's what you were saying.
Yes, basically that's what I'm saying.
But this is on the way.
Okay. Sorry, where did I leave it? Okay. So this is a link to the data. And essentially what we're doing here is accessing the metadata, Stack metadata for it. What we will do then is essentially open up this data as well. But this is essentially like as you can see over here, what we're doing is we're opening up the collection that's somewhere in a remote repository, and then we're getting the items. And these items for that data will have assets, and it will be a direct link to the data so that we can start using it from Stack. Okay, that's using static Stack APIs directly, but I guess one of the problems there, and one of the main things that the Stack API definition and standard adds, is a way to search through the data. So the extension essentially adds an API for search for other things as well. And if you use non-static Stack items, so if you basically have a hosted backend to serve those Stack APIs, and that backend follows the Stack API definition and standards, what you're able to do is search through Stack repositories. EarthCODE has one as well, but just to show another one and another Stack repository, this is the element 84 Stack catalog, and what we're able to do here is do something different than what we did. So previously we just wrote the search ourselves. If you're using a dynamic API, what you're able to do is pass directly query parameters as such, and essentially search through things like directly search for collections, collection names, pass a bounding box directly to the data, date time for what you're searching for, and so on and so forth, and it's going to try and access those images for us. So what we're doing here specifically is we are searching for collections for Sentinel-2 data within this bounding box area for these dates. And we're passing essentially we're passing a custom query which will look through the stack metadata for us. So this one doesn't have a property for it, but the stack metadata will have, let me just show it, it will help. Okay, just gonna open up an item. What essentially it's going to do is look through the stack metadata to find us a, oh, sorry, this is matched. So it's looking for, just give it a second to load, but essentially what it's doing is looking for the stack properties and then filtering based on this query. So we're able to use essentially the stack metadata to narrow down the search we're trying to make on the data. It's taking quite a while. Okay, never mind, but that's what it's trying to do. Okay, so going back to basically how do we do anything with this data? We had this stack data for the ceasefire cube just now. And essentially it's taking quite a while to run anything, isn't it? Okay, cool. So, and we had this stackfire ceasefire item over here, and it had some assets and data into it. So essentially what we can do is directly pass this URL to Xarray and open up the data directly. So what we're going to do here is just build the URL. Essentially this is what this line is doing because there was some errors with the way the extension for storage was defined. So essentially it's just building up this URL of the ZAR file, and then we're passing it to Xarray to open it up, which we'll talk a bit more about in a second. So this directly essentially fetches the ZAR data, doesn't load it at the moment. We'll talk about lazy loading in 1 second. Essentially goes through and then makes the data accessible and usable for us. So we can then, for example, as the workflow over here goes, which we'll do in a second as well, visualize some of the data and start using it. Okay, and now we'll talk a bit about how to actually use the data and the tools we're going to use for, the libraries and tools we're going to use for the data itself, for exploring the data itself. Annie, would you come along to just start with the Pangeo bit?
Can I ask a question?
Yeah?
On searching, how do I find the vocabulary for search? Which parameter I can search for individual data sets easily?
So there are queryables in Stack that get exposed by the API. The typical ones you would see, so you would be able to mostly search on things that the metadata already has, like properties, and it depends really on the extensions that the catalog exposes. So for example, EO.
So I need to look at the exposure extensions, and there I see
which ones are available and what you can do on the actual catalog data. So for example, I can't show you the data over
Is there
here.
already a Python tool to list all the possible query elements?
You can
Yeah.
You can query available for the given.
Sorry, Anine, you were saying?
You can see all the metadata available for a given catalog, so which gives you what you can query.
Yeah. Hope that answers the question.
But like the minimum should be for the element, like the standard stack default without extension. You need to fulfill when you have a stack.
I'm looking at this line 9 here in this example where it says for Sentinel-2 data and looks for cloud cover.
Yeah.
And what's the fastest way when I know I have a collection or catalog to find the description? Is it also programmatically available that I say describe, like or get capabilities or something?
Yeah, I think so. I don't remember what I heard, but yes.
Yeah.
You can see.
Conforms to is, I think, your, and, well, not conforms to, there should be an extension, but.
But you have the property that the icon level,
I just checked the API.
yes.
Yeah.
Yes. Not sure this is true. We should add this example.
Yeah, that's a good shout to add for next time.
We use your.
Yeah, you want to just go from over here?
So we have a break now.
Yeah, so maybe just introduce the slides and let's go for a break and start off with the X-array bit.
Yes. Who knows about the Banjo community? Okay. Oops. So this is what we're explaining here. Like this is global, this is open, and open is very important because we don't want the community to be locked in, but we don't want the community to be locked in with tools, with platforms, and any ecosystem that would prevent you to move to another one in the future, especially if this is not open. So this is open community, open platform with a user interface, scalable compute, which we will see today how we can go from like the laptop and a small area computation to a much larger computation. So this is one of the platform that hosts Pangeo, and this is the one we are using in this tutorial today. So you have to understand this is like, because it's open platform, it means you can deploy this platform anywhere. Like a data provider can choose to deploy a Pangeo platform on their own facilities. And this is what EuroDataCube does. They are providing the data and compute infrastructure to deploy this Pangeo ecosystem. But what is really important when you choose a platform is also to look at what data they have, because that's what you want to have most important. Like the data is driving the platform you are choosing. Because if you go on a platform and you have data and you have storage, GPUs or whatever, but no data, you will have to download the data and it will take forever. And even if this is cloud data, it costs quite a lot. So something very important, because you have this Pangeo infrastructure on EDC, sorry, I shouldn't mix. You can request, here today, you get it for free for the training. But if you want to have it for your research, you can request the same infrastructure through the network of resource, which is sponsored by ESA. And you can select, so here you have, you don't show the EDC here, because it's Mayo. But you can scroll down through all the different resources in the network of resources, and you will find, if you search for Pangeo, you will find the one, and you can request. It's very simple to request resources from the network of resources. You mostly have to fill a form, and it's usually super fast to get it, especially if like the main goal is to get access to this platform, so you prepare your data and then you can publish on the EarthCODE. So this is a community of developers, scientists, of users, so it means what we want is not only to have like end users using data or software, we want also to have the developers of the software, and we want to have them close to the end users, so we can identify what are the needs of the end users and what software or like packages we should develop, like Python packages. If you know Xarray a bit, it's developed by many of the Pangeo community developers. If you want to join us, we have like community meetings, which I think now they are alternating on Tuesday between 9 and 4 o'clock CET or CEST, depending on the time of the year. And it's usually super informal, at least in Europe. And in America, it's a bit more formal in the sense they have like showcases very regularly, where you can see what others are doing, and you can also showcase what you are doing, and you are strongly invited to do it. Should I use this one? Maybe we can skip, because so one thing that is really important to remember is one of the goals of having this open platform is also to promote the reproducibility of your research, if you are a researcher or if you are an engineer or data engineer, so that you can reuse what others have done, and you can also reuse yourself what you have done maybe like 2 or 3 years ago. So we want to have like open, reproducible, and scalable science, which is also exactly what the EarthCODE initiative does, but with different set of platforms, not only Pangeo. So how do you make a platform scalable? So you want to have like modular components. And if we start with the user interface, we usually access through the Pangeo ecosystem via Jupyter ecosystem. So they don't have their own like a user interface. They are using I think they are using Jupyter Lab or Binder, and for being modular for accessing and analyzing the data, we have the data model. And we are based everything on top of Xarray, which is an open source package for accessing like gridded data, mostly. And this is also developed by many of the Pangeo software developers. And if we want to scale, we also need to have scalable compute. And the idea in Pangeo is to be able to run on your laptop, where you don't have a lot of resources, and then you move on the cloud or on a HPC, high-performance computer, but without having to change your code a lot. Because otherwise, it's a pain every time you want to go and scale. So you have like a small scene, and you make your algorithm on your laptop, and then you want to run it for a very large area. If you need to rewrite everything from scratch, it's a lot of pain, and usually you waste time and you include new errors. So this is like data model, user interface, scalable compute. This is more what you see as an end user or what you are interacting with. And then behind the scene, we have the system storage and the resource management, which is really how we store the data or how we manage computing resources. And of course, it will depend on where you are on a laptop, on a HPC, or on the cloud. The storage system, the underlying storage system is different. Because it needs to be efficient for this given infrastructure. But usually, at least we don't really need to know all the details. That's it. If you want to collaborate, you are more than welcome to join and collaborate as an end user, as a developer, as a scientist. So there is a bit of everything for everyone. I think we will see later the task, so maybe we can skip. But the idea is we will see how we can scale from a very like a laptop-like computation to a huge number of computation with a Dask cluster. And you will see this is quite transparent. There are a few things to learn, but this is quite fast and efficient. So I think we can maybe stop with this, no? Or
maybe just give a final one as well. So
which one?
yeah, just this one.
Sorry.
Oh. There we go. This one.
Oh, yes.
Okay, maybe just to
the infrastructure, yes.
just to talk about what is the key component sort of in the Pangeo stack. So there's a lot of libraries that are sort of tangential to the ecosystem. But when you start working with the Pangeo stack, there's 3 key components that kind of make the core of it. And then the rest are, well, the rest are very important as well. But essentially, those 3 are the compute engines you would use. And the first one is essentially Xarray, and that's your effectively, that's basically the API and interface that you're going to be using to manipulate the data. It's pretty much a pandas-like interface. So most of the pandas queries you would use essentially in Xarray as well. The difference is that Xarray provides you a common way of working with multi-dimensional data sets and multivariate data sets much more easily. Underneath, it's still NumPy. It's still using the NumPy APIs, but with different implementations. Okay, then what we have is the actual compute and distributed compute, which happens through Dask. And Dask is similar through Spark, or you might have heard of Ray as well. The idea is essentially that the workloads you're trying to run get distributed across your own computer and then across, well, and scale even to clouds and so on. What it does, it implements essentially all the NumPy APIs for that are for vectorizations that would typically run on your core, on one of your essentially CPUs. They create the distributed algorithms to run on many different threads, CPUs, and distributed algorithms, basically. So if I'm using, let's say, something from sklearn, there might be an alternative for a distributed algorithm of the same thing in Dask, and that's the idea essentially. It provides that distributed compute engine. And then on the back end, typically how data is stored in the Pangeo ecosystem and the data sets we work with are ZAR and are saved as ZAR files, essentially chunked data sets that are able to scale. And the whole idea is you have, instead of just having one monolithic file, you have one chunked file that you can access different ranges from, depending on what you're trying to do with the data. And we're going to get into a bit more detail about how that works and to the next bit of the workshop. But for now, let's have I think there's a coffee break from 3 to 3:30. So when we come back to it, what we're going to follow up with is hands-on with Xarray, ZAR, and Dask, and then get into an actual example of using the data we were just looking at and loading for wildfire analysis. So we'll see you in about 20 minutes, everyone.
pushing. Oops. Okay, so let's start again. Do you still have the? That's the wrong room. So one more, isn't 401. So we will start a bit exploring the data cube with X-array. So we want you to go on the Jupyter lab of EOX and open the X-array 101.
It's under
This tutorial.
BiDS'25 tutorial, and then if you go into Pangeo 101, and then if you click on X-array 101 notebook, that's where starting off.
Yeah. Let me know if you have any problems to access it. Do we need to repeat where you can find it? Or yes? So if you click on the main BiDS tutorial, then you have Pangeo 101 and then X-array 101. Yeah? All good? I still see a few people trying to find it, so maybe we give a few more. Yes, give a shout if you need help to get. All good for everyone? Yes. Yes, all good?
I think everyone has it.
Okay, perfect. So then what we will really try to it's very important that you understand how X-array works, because all the other packages are usually built on top of X-array. So I think we asked already before if you were familiar with X-array or not, and there are a number of people that are not familiar. So we'll go through, and you can also go back later. And I think you also go back to it when you explain later on.
Example.
Yes. So we will import X-array, which is here the most important library or Python package we want to look at. And X-array here, we will use it to open one file, and this file is a ZAR file, and this is a ZAR file from the EarthCODE catalog, but instead of going through the stack catalog, we can access the data directly, providing a URL, which is really like where the data is located. Of course, it's difficult if you don't know where the data is located. You cannot open this data, and this is why you usually use a stack catalog. So we are using this X-array open dataset, open _ dataset, and with this, we are opening one dataset, which is this one, the ceasefire.zar, version 0.4, and we pass a URL of the file, which is a remote ZAR. And we are saying this is a ZAR file. So ZAR is a data format, which is cloud optimized. And it's like the rest is some option, which says how the ZAR file has been created. And when where is it? It's moving up and down on this. Yes, okay. So when you execute this command, what do? We don't load the data in memory. So the first thing is we only read metadata that are on this ZAR remote, and we are exploring the metadata, and we will only load the data in memory when we need to access, for instance, when we plot, when we do some computation, and only when we compute, not when we prepare the computation. But so what is important here is an X-array. When we open a data set, we have an X-array data set. And this is very characteristic of an X-array. We have dimensions. So here we have latitude, longitude, and time. So we have this is what we call a data cube, which is what you have shown before on the graphical interface. And we have coordinate, which is the coordinate system used for this data cube. and we have the latitude, the longitude, and the time, and each of the coordinates, they have the dimensions that are defined here at the top. So here we have a latitude, longitude, and time, and then we have data variables, and we have many of them. Here, I think we had like 59 variables, if I'm not mistaken. And each of these variables, they have different dimensions. So they have like data cube as a time, latitude, and longitude. They are float 32, which is not so important. But one thing that is important here is that we can see it's like the chunk concept. So it means we don't load the data in memory, but we still, with the metadata, we know already that the data is chunked. So it's like cut in small pieces, which means when we will do some analysis, instead of having everything to load into memory, we can access one or several of these pieces and make the computation. And this is how we parallelize with Dask, which you will see just after. So we can put several chunks into a Dask worker, and that's exactly what you will look at. But by default, when you open it, it will already show you as a Dask array, even if you are only on your laptop and not doing any computation, parallel computation. So these variables, how do we access them? So yeah, one last thing is when you open a data set, you have a bunch of metadata, which are useful usually to understand what is the data, what is behind the data. And this is very similar to what you have seen in the Open Science Catalog. How do we access the data? You can access the coordinates one by one. So you can put the name of the data set and a dot and the name of the variable. And the variable can be either a coordinate variable or a variable name. And when I execute this here, you will get a data array. So we have a data set, and each data set will have like a bunch of data array for the coordinate and for the variable. So when I access, for instance, LI, which is a leaf area index, I access, oops, this is here, I get as a, so I don't know why I have this. Okay, I get a data array, and it has the time, latitude, and longitude, and we see that we have these chunks here, which we can exploit for parallelism later. And we also have new set of metadata, which are important, again, for like the stack catalog. You can access it via a dot, like we did here, ds.lai for accessing a variable. But you can also use square brackets and put the name of the variable in quote, which is what we do here. So it's easier. Instead of NumPy only access data via indices, like 0, 1, 3, etc. Here we access data through names. So it means when you write your data analysis, you access the data and you know exactly what you access because you access it via the name that is familiar to you. And we can also get the attributes with a dot at ATTRS, which gives you like a dictionary-like or JSON with the name of the attribute and the value. So it's a standard dictionary. So as I said, when we load and open data, we don't load the data in memory. So everything I have done so far, I just looked at the metadata and exposed the metadata to the user, which says this data has this set of variables. They have latitude, longitude, and time. But so far, I did nothing. I have no data in my memory. And to give you an idea, is here we are showing you with NumPy the size of the product. And here, this is, if I compute, this is nearly like 3.7 gigabytes. But I have no 3.7 gigabytes. I don't even have this amount of memory on the machine. So it means when I will need to do some computation, I cannot load the entire data set in my memory because it will be larger than what I have on this machine. And that's the main goal of this chunking and this parallelism. we don't want to handle all the different chunks, but we want to have an ecosystem that helps us to parallelize easily. So here, when I do the data, it's the same. I see the size of the data, but I can see below, if you look at the memory here that is used, I don't have 3 gigabytes of memory used. I have only 1.2 gigabytes used over the 3.60. And there is no way that this is the entire data set, because it would be already far bigger than what I have. So when we access this like data, it's not accessing data, it's only accessing the information about the data. We can, with X-array, select. So what the idea is, you want to only load in memory what you need to load for your computation. Let's say if you have a data set covering the entire globe, but you only want to have a small area over Switzerland, there is no way you want to load everything in memory and then select. So what we do is we select, and then when we need to do the computation, we only load the data we need over the area we want. So for selecting, it's exactly the same. So here we show you how to select using like the NumPy approach, if you are used to NumPy, like 0, 1, 2, 3. And it's very cumbersome, because here if I select LAI 0, 100, 100, can you tell me where I am on latitude, longitude? We don't know. That's what is very cumbersome. So here, when I do a dot load, I load the data. But in the X-array, we have something which is very nice. We have iCell methods or cell methods. So iCell method is when you want to use the name of the coordinates, for instance, for accessing, filtering. So for instance, when I do ds.lai.icell, with the I cell, it means I will select by index. So I will use the name of the coordinate, like time, but then I will give an index, like time equal. I will not give a time. I will give like 0, 1, 2, 3, 4, 5, and it will be the index in the array. And the same for the latitude and longitude. When I say latitude equals 100 and longitude equals 100, I'm not accessing the latitude at 100, because it doesn't make much sense. But what I do is I accessing the index in the latitude coordinate corresponding to 100. And this is already a bit better when we want to access and select data. But there is another even better way, is instead of accessing through indices, I will access through the values of the time, of the latitude and longitude, for instance, the value of the coordinate, which is what we do here. I will select, and I want to select a time, but I want to select a specific time which I know as a human, like a 20, the 8th, is it on which? The 8th January of 2020. And of course, in my data, maybe this is not the exact value I have in the coordinates, so I use nearest as a method to give me in the data cube what is the closest value for this specific date. And the same for the latitude and longitude. And here, this is even more important to use methods for latitude and longitude when you are selecting like float values, because it's probably not encoded as 46.3. Maybe you have 46.3 through whatever, and you will never, it will return 0 if it doesn't find the exact value. But if you add method equal nearest, it will select the nearest method, the nearest latitude and longitude. So here we are selecting one point, which is the closest to 46 degrees, because here we are in latitude. It's not I cell, but it's cell, and longitude, which is 8.8. And then we select the first time, meaning I don't really care which value is the time. I just want to check the data. Oops. And here I will, where is it? Is here. Oops. What it returns is still a data array. So every time we have a data set, but when we select or when we access coordinate, we have a data array. And only here, again, I'm not loading anything in memory. but only when I select, for instance, when I load. So for instance here, I will access the exact value at this coordinate. So here, for instance, I say, if I select 100 index for longitude, I can get the value with dot longitude and the value and this item. So it's minus 154.875. So it means if I don't use all the digits, I will not be able to select. In X-array, any question on X-array so far for the selection? So you have the selection per coordinate with iCell or cell. And the difference is you always use the name of the coordinate when you are filtering, but you either use an index, which is 0, 1, 2, 3, etc., or you use the value in the coordinate data set. In X-array, what is nice is you can access all the matplotlib, if you are familiar with matplotlib, for plotting in a very similar way with a dot, like as a method from X-array. So for instance here, instead of plotting the entire data set, we are selecting with the dot cell. So what do we do here? We are accessing one variable, which is this LAI variable, and we could use squared bracket and quotes. Then we are selecting, and what we are selecting is a slice. So when we select a slice, it means you select more than one value. You select all the values between two minimum and maximum value. And as you can see here, we have the like 65.5, 25.5. Why? Because when you select value with a range, you need to select the values in the exact order that is stored in the data. And if we go up, here, you can see that the value in the latitude is from 89 until minus 89. So it's going down instead of going up. So very important when you select. And here is going from minus 179.9 to the same but a positive value. So that's something you need to be careful when you select a slice. If you select in the wrong order, you will get nothing because it won't be able to find any data. So here we are selecting an area, and then we are selecting a time, and then we do a dot plot. And when we do a dot plot, we are using matplotlib, and it will plot the data, assuming like using the coordinate of the data array. So the LAI here plus the latitude, longitude, and we'll plot with a default matplotlib or X-array matplotlib visualization, which is what we see here. And we see like this is an area over France and here over Europe. And we have the leaf area index. So when we plot matplotlib, because it's an X-array and we are following like the CF convention, it will try as much as possible to get and use information from the metadata. So it will give you the time as a date. It will give you the longitude, but it will give you the long name if you add it in your X-array. So here it says longitude in degrees, and it will give you the meaning of the LAI variable because it is in the metadata. If you don't have it, you will not plot it. So this is why metadata is very important. What else? If you are familiar with NumPy, you can do exactly the same computation, but with an X-array. So it's very similar. If you know already how to add, subtract with NumPy, which is very similar to scalar addition, multiplication, and other statistics, it's very similar here. But again, when we are multiplying something, we are always working with this data array because here we have selected one variable. So we are getting, again, a data array, but with multiplied by a scalar and adding 1,500, which is handy when you want to scale your data. And again, here we are not really computing yet because we don't really need to compute. And we can do some statistics, a min, max, and mean, which we can do as usual. And we are plotting here. We see the last one, which is a mean value. And it's again a data array. But we can do a lot more than that. So here, this is like the basic, like NumPy statistics you can do with an array. But in fact, what is very, very powerful, you can aggregate data over several dimensions. And this is what we call this group by, which is very handy if you want to group the data over 1 or 2 dimensions or more. And, for instance, compute a minimum or maximum value or average. So here what we do is we are grouping this LAI. So remember, if we look at the coordinate, which is here, we have latitude, longitude, and time. So when we are grouping, we need to group the data over one of these coordinates. So we need to, here, we want to group over time. And here we do even more. Instead of only grouping, we need to specify how we want to group over time, and we want to do like monthly mean. So we can specify the dt.months to say only take the months. And then you do the average. So here, because we will do monthly, like average per month, we will have 12 value because we have 12 months in a year. And every value will be an average. And we keep the latitude and longitude because we only grouped over 1 dimension. Don't know if I execute this one, actually. This is really great, this group by, when we want to group per coordinate. So you can only use a group by for a coordinate variable. So here for time, latitude, and longitude, because this is what we have in the coordinate. Like when we had this coordinate here, we have latitude, longitude, and time. If we want to group over another, for instance, variables, or anything else, I cannot do it with a group by, and I need to use another method, which is a where statement. For instance, if I want to select or to mask the LAI over, but only keeping the ones that are greater than 1.5, then I will need to create a mask, which is true and false. And then I can select and plot this one using exactly the same method. So it's going up and down. So here I got a mask, and I don't really see much differences, but it will put some non-value where you have where the LAI is lower than 1.5. And then when I plot it, we will only see like this is for the first time, because remember, when we select, we still keep the time, so I need to select 1 time. And when I plot, I only see values that were greater than 1.5, which is true. When I look at the color bar here, it starts only from 1.5. So this is when we want to filter, but per variable. And if you have a data set where you have many variables, you can filter using another variable of your data set. And here, this is one way we do exactly the same, but we are filling with 1 or 0. So here, I keep the value as they were in the array, in the data array, and I just none everything which is below 1.5. But here, what I do is I put 1 or 0, so I will have like a binary map. And that's what I have here. And this is more or less like the main X-array methods you can use, or the most basic one and the most used. I really encourage you to look at the X-array documentation when you are looking for something, rather than implementing yourself from scratch, because there are many methods that already exist. Do you have any questions? Anything that you find odd or no, nothing looks fine, logical, perfect. Because then after, we will see also how to scale, yes. Exactly using the same thing.
Cool. So that's how X-array works in a nutshell. And now to dive a little bit deeper into it. So maybe one thing that to clarify, one thing that really makes X-array make sense if you've ever worked in the pandas NumPy world is it's using the exact same structures as pandas, where you basically have just to find one of the open, where you basically have one sort of data set, which is like your pandas data frame essentially, with many internal data series, which are the data arrays. So you're basically like replacing those two ideas with a multi-dimensional version of them. So okay, in pandas, you would have, the typical visual is you have a table, and each table has values, and each column is essentially your series data. In X-array, that just goes the level above with multiple dimensions. So you have one data set that has multiple multi-dimensional data arrays. And the coordinates essentially here, they're your indexes for the data. So that's really the key concept of what X-array does in a nutshell. And now one thing that you would have seen if you were looking very, very closely is at some point we do this dot load over here on the selection methods. So, okay, up until this point, if we look at this data, for example, what this query will return, it returns some sort of a weird X-array data array structure that tells us that it holds some float and NumPy, NumPy float in the array. And we don't really know what's in there. So typically in the pandas sort of workflow, what you do is you provide it, let's say, filters, queries, group bys, you group the data, you filter it through, and you sum it up, you do your calculations, and at each step it does a calculation for you. So after you run a command with pandas, let's say sum, it's going to immediately sum it and return a result. What's happening with X-array is, especially when you use a Dask as a compute engine, there's many other engines as well, but basically like just there's also NumPy directly. But when you use Dask as a compute engine, you have something called lazy compute. And essentially what that does is every command you give X-array, like for example, over here I'm doing a selection. Over here, when I was showing something, she was, again, when she was plotting data, she was first selecting an area of interest and then plotting that area of interest. When you execute each command here, it's not actually doing the computation on it. It's planning what it needs to compute in the background. And essentially it's passing these data arrays, metadata in between different compute stages, and it's trying to do basically a computation in the background, and then it's optimizing it. That's essentially what Dask will help with when it comes to that. So like, for example, here, when I type in load, what's going to happen is it's going to go away from using Dask, and it's going to directly load the data as a NumPy array. If I can, it works better with multi-dimensional data. So maybe just yeah, okay. Let's look at this one. So a.ali. So let's look at what happens without load and with load. Give it a second. Okay, we've loaded the data, and as you can see, there's some sort of an array here with the data directly, and it's a NumPy array. When we don't load it, what's going to happen is this data over here is going to get computed as a data array, and it's going to be a Dask array in the background. Okay, so what is this thing, Dask? Why are we using it? What's happening when we're going through different commands? So to better understand that, we first need to get an idea and some intuition about chunking and what these chunks mean. So we have something called cloud native chunked formats. And the concept of that is when you have, I'm going to load it directly. There we go. Okay, when you have your data, you can have it as, this happens on disk typically when you store data either way. So there's some idea of chunking your processor, your memory. The data is not going to be in one big sort of data set. It's going to be in either strips or chunks or tiles, so that then those tiles can get processed and gotten retrieved by the CPU in some shape or form, essentially. It's really the same idea, but pushed up into the cloud. So instead of having like basically the whole data downloaded, you download individual chunks, you separate the data out into different cuts, and then you do computations over those individual cuts, and you only get the cuts that are of interest instead of like using the whole data sets to do computations over it. And essentially that's what chunked formats help out with. There's several like these. NetCDF, for example, offers some chunking in the background. There's some chunking, but typically you would use something like ZAR or CareChunk if you're trying to make the data more cloud friendly. And why that is basically when you use a format like that, the data will be stored as, each individual chunk will be stored as a separate object, and it would be able to retrieve only the objects of interest directly by looking up the metadata. So what like essentially a ZAR store has, if you save your data as a ZAR, is it has metadata and it has the individual chunks. Those individual chunks are your essentially the variables you would see here, over here, organized in some fashion, right? Each individual chunk is a separate file that contains basically the data that you're trying to look at. And there's one central, if the ZAR file is consolidated, there's like one sort of central metadata bit that tells you where each chunk is and what it corresponds to. So when you're using something like ZAR or chunk formats, what's happening is our X-array is like interpreting it. So it's first reading the metadata that tells you what every chunk is, where it's located in memory. That might be somewhere on the cloud. It might be somewhere on your, it might be somewhere on your computer. That's close. And essentially, it's giving you the location, how many bytes it has, what the information is, and other metadata about those chunks. And that's how it's calculating basically this chunk over here that you see. That's how it's calculating essentially the total size and shape and everything else there using this metadata. What's happening then in the background when you're using something like these cloud native formats or chunked formats in general, is Xarray is going to use an engine in the background that only pulls the chunks of interest. Now, you don't have to be using DAS per se for that. If you use regular NetCDF as well, that's what happens. So, for example, if I'm only loading a data set that, like locally, let's say, and if it's a NetCDF data set, it's still going to try and like only load the chunks in memory that are of interest. It's not going to load the whole data set necessarily for me. So Xarray is doing some of the smarts in the background for you. Now, using the different drivers and engines that it has, and that's what they essentially do. They provide and give Xarray a description of how the data is stored and, well, wherever it's stored internally and how to process that data. Okay, so a chunk, essentially what it has information about how large it is. It has dimensions, as in that essentially how your data is broken down, by which dimensions. So let's say if we look at something that's a three-dimensional chunk, it might be, let's say what's happening here is we have a data set with these dimensions, and the total is 3 gigabytes. A chunk is essentially all the times for a particular period. So we have 966, this is the time dimension. We have 966 times. What we see each chunk is it has all the times for the latitude and longitude of 180 and 360, like a shape of 180, 360 pixels in it. So for a particular region, each chunk is going to have the data for all the times you have in your data set, essentially. Why is the shape of the chunks important? Is because this is kind of going to, really this is the way you optimize how to process your data. So if you're doing, let's say, time series analysis, I'm just going to finish this up and take your question now, sorry. If you're doing, let's say, time series analysis, what you want, and over particular regions, what you want to do is like have as much of that data accessible to you, so you don't have to do multiple retrieves for that data, especially on the network, because there's a lot of overhead for it. And you want to have the chunks that you need for the compute you want to do over them at the moment where you want to do compute, to avoid essentially having to fetch data all the time, different instances. So for example, right, if I have a query, which I don't have an example of over here, but if I have a query that essentially does time series analysis over, let's say, this region of my map, I'm going to essentially be able to pull that chunk and over this 200 megabytes directly do my analysis, and then I don't have to pull any other chunks. And that's essentially the idea of it. If I have it separated, let's say if I had another way of shape here for my chunks, if I had, let's say, 100, let's say I have one per time and I have bigger sort of geographies in it, but I have a smaller time step, what I would need to do to have like a time series over all the years, I would need to essentially go and make a new fetch request for the data for each separate chunk at each separate time step. It's just because the architecture of the data is separated in that way, which makes it harder to do different things with. Sorry, you had a question?
Yeah, I'm not sure if I missed it, but where do I define the shape of the data?
So essentially that happens when you save the data. And so, well, there's two types, two things here. So this chunks over here is what does it. This is where you define what you want your data to look like. So what essentially what this parameter does is it loads chunks that are saved locally to the file. So whatever you save the file, it's going to use that chunking architecture for your X-array representation. What you typically do is when you save your file as an ZAR data format, you specify the chunking architecture you want to save it as, and that's how it creates the chunks and everything else. And then basically when you pull those chunks, what you're able to do is either use the architecture that was initially saved as. I'm going to show how that gets. Oh, actually, I'm just going to quickly scroll to it over here to show you how it is, how you get there. Put it at the bottom over here. Okay, there we go. So essentially, right, it's very easy to save essentially data as ZAR, but basically how it works, like I first chunk my data, right, and I set the chunk over here if I have whatever data I've loaded to X-array, and then when I save it via using something like toZAR, which creates the file, that's essentially the data that's essentially how you set the chunking architecture on it. But then what you're also able to do is if, let's say this doesn't suit your analysis and you want to do something slightly different, you can rechunk the data, which is typically like a very expensive operation to do. You don't want to really be rechunking data all the time because you're going to have to fetch all those chunks and then in memory separate them and then distribute them. And especially if your rechunking doesn't align the chunks themselves, you'll have something like, if you look at it visually over here, if let's say I'm looking to make a query of this space over here, it would be much easier for me to grab this location of the data all together in one go, and it would be much more awkward for me to fetch this location of the data as one chunk, like if you see in the middle of it, because what will happen is I'll fetch all these chunks over here, half of the chunks over here to the left, but I'll only end up using half of the data within those chunks, right? So that's why we need to be careful also when rechunking. Okay, how can we rechunk if, let's say, we want the data in a separate, in a different format? What we can do is basically place it over here and say which dimensions we want to chunk how. And that provides different options for that. Like basically what you would typically do is, depending on what machine you're working at, of course, and what your workflow is, but the typical workflow is you would use whatever the chunking architecture is for the data. And this is what this does. When you pass in empty square brackets, it basically loads the native chunking. When you do -auto, what's going to happen is essentially, and you see a bunch of warnings popping up, but when you do this, it's going to essentially try and rechunk it in a way that it best see fits. Let me just find out. There we go. In a way that it best see fits. So as you can see, it's like using a different chunk now. It's at 785 time steps and a smaller sort of area. It rechunked it automatically by itself, but what happens there in the warnings you'll see is essentially telling you it's probably going to have rechunking after load. It's going to need to rechunk it, and it could degrade performance if you try and load the chunks and request the chunks using this chunking architecture. So
maybe it's good to add that you can just inside that, as the example you showed there, further down, you can specify the size of the chunk. If you know beforehand you want this chunk by let's say, as you showed.
Yeah, you can basically type.
You can type it into that the curly brackets there.
Yeah. So what?
The size of the chunk and not the size of the.
Yeah, just to visualize what, well, just to do what he's trying to. So let's say I want to chunk my data in a certain way. I can directly pass in something like this. And what this is going to do is, if I look at the data variables over here, is I'll have 100 time steps per whatever the chunking architecture is of my original data. So you can override the chunks, you can do a lot of things, but again, what's going to happen in the background is because the data is chunked in a way where you have 966 time steps per chunk, it's going to first pull all of that data and then do something with it, which is not very efficient. So long story short, chunking is important, and it's the way you speed up all the computations. Okay, what you can see basically in this is a couple of things as well, just to note, is you can see the size of a chunk, and you can see the size of the overall data array. Something to note as well is that this is different than what it is on disk, because the chunks get compressed. There's a lot of filters and optimization algorithms that then get applied. This is the size of the data that's going to be needed when you load a chunk in memory. So, and I'm going to show you that when we actually save a ZAR file. Yeah, so that's one thing. We're able to see the total size of the chunk. And any questions just before I go on ZAR? What's the main idea behind chunked formats and so on? Yeah?
So maybe the notebook mentions ZAR and also chunks NetSigniff. Is COG also supports?
Is what?
Optimized geotiffs.
Yeah?
They also support it as an...
Yeah, so you can load geotiffs in ZAR via Xarray as well directly. So and there's also specialized libraries for even handling them further. But so COGs and geotiffs and raster data generally is like one of the first use cases for the geospatial sort of world. And ZAR and generally this sort of chunk format with multidimensional data is like the sort of up-and-coming thing that's happening now. But it originally started with COGs and geotiffs.
Native formats, and COG wasn't mentioned anyway, so it's kind of...
Oh, because it's just focused more on scientific multidimensional data. But yeah, no, COGs definitely, you like basically work in a similar way. Slightly differently though, because you're requesting ranges and the metadata is just arranged in a different way in one TIFF file.
And maybe step further, because COG, of course, is limited because there's no time dimension often.
Sorry?
Yeah, because COG is limited because it doesn't have the time dimension.
Yeah. So how you would typically work with COG files in this sort of multi-dimensional world, let's say if you have like many COG files and you want to kind of do the same thing here and with this ecosystem, what you can do is essentially, and that's sort of what we showed earlier with stack and data access, which we didn't go into too much detail because I'm going to go again in the example. But basically, we are over here, we're getting essentially quite a few items. Just continue over here. If I can run it through here and show you what's going on with COGs. Okay, so let's say here we're finding 6 data sets. This is 6 stack items. And just to overlay those 6 stack items, this is what the stack dimensions are. For the GeoTIFF world, you have many other tools as well to help you out, like stack load, for example. And what this is going to do now is essentially take those items that are different time steps. So maybe I'm just going to load it just to show. Well, actually, this is a one-time step that it's loading. But basically, what you're passing here and what the stack load does is essentially taking those geotiff items and then stacking them on all together to create this data array, a multi-dimensional data array. And you're essentially using stack and geotiffs to form like the multi-dimensional data that you're trying to examine. And then you can use the same tooling, same stacks, same workflows to analyze that raster data.
That's still, do you have a stack catalog containing a lot of geotiffs as items? Having time dimension, is it possible to load that directly as data sets in return?
This is what's happening here. So basically, and if I got your question, the question was like if you have many cogs that have over time and you're describing as a stack, can you load them in memory somehow as the X-array? Yeah, that's what's happening here. So essentially, this over here is pointing towards this data over here for Sentinel-2 images as geotiffs that are described in stack. And what's happening is first I'm getting 6 items, essentially for different times between this time period. And then what I'm doing is I'm passing these items to load them, essentially to load them in as an X-array data array. Well, data set, I think. No, sorry, yeah, data array. So essentially, that you kind of have access to the same tooling, same workflows through the same APIs, if that makes sense. And that's what the whole PanGeo ecosystem is trying to do as well. Okay. Any other questions about ZAR? Cool. Okay. Now it's loading those. It's loading those chunks, right? And it's doing this computation lazily and so on. But this is happening. This will happen if you use netcdf, if you use cogs. It will be trying be smart about it. Nevertheless, what sort of computation engine you're using on the background, just because the libraries work that way. So if you use a netcdf engine, it's gonna still load local chunks in memory and try and do stuff with them. The problem with it is that it will try and load. Let's say if you have an area of let's say that's 10 gigabytes, and you try and load that whole area into memory, and you're just doing a subset again. What's going to happen is for all the computational algorithms that you're doing, let's say if you're doing an average, if you're doing a sum, it's going to load all of that in memory, and it's going to break basically your machine because it's going to give you out of memory, and it's going to crash the kernel, and it's going to stop. So no cigar, it doesn't work that way. The X-array doesn't implement by itself those distributed algorithms. To essentially load data and work with data that's larger than memory, people have come up with a library called DASK, and that's what it originally started out, working with data that's larger than memory. And how it does that is with distributed algorithms. So you have a distributed algorithm for a sum, you have a distributed algorithm for an average, you have distributed algorithms for, let's say, clustering. Let's say if you're doing something like, if you're using, let's say, sklearn as a library locally to do all your analysis, that will use NumPy underneath, and that's going to be very much sort of loading everything in memory and trying to do it all together. Might be a bit smart about it, but it's not trying to do it in a distributed way. With Dask, it's going in the other direction, and it's trying to make all those APIs, all those sort of computations distributed in some sense. So you're using a distributed sum algorithm, you're using a distributed average algorithm, and so on and so forth. And it's basically those APIs for the computations, it's replacing them with some distributed form of that algorithm or that sort of computation you're trying to make. Some limitations to it, but essentially that's the key idea behind it. And why that's also very useful is because it's not only, the idea is you will have the distributed algorithms, and that's great because you can load data that's larger than memory. So let's say I have a 10 gigabyte computation, I'm looking at a region that's got, let's say, a leaf area index of 10 gigabytes, and I'm trying to get an average of the whole place. I can just get the average of every chunk and then combine them and get an average like that. Or well, whatever the average algorithm is for the distributed Dask. And basically what Dask is essentially going to do that. But the great thing about it is let's say I want to do it over 100 gigabytes, or I want to do it over 100 1,000 gigabytes, I can basically use the same distributed algorithm and give, like, essentially give more compute somehow to Dask to run it across, let's say, an HPC cluster, where I don't have to have one monolithic big HPC machine, but I can have many different smaller machines or containers running in, let's say, something like Kubernetes, doing those small computations one by one, and then combining it somehow into, well, getting the larger result. And that's where Dask sort of evolved. It went into from just doing out-of-memory computations to like doing larger than, well, distributed cloud computing. And sort of like on par when it comes to Spark or Ray or any of the other libraries for the same thing. So that's how it sort of evolved and started. How it works is essentially, it's integrated very transparently and smoothly into Xarray. So as you see here, you weren't really doing anything different with Xarray, and you were using the Dask arrays in the background. How Dask essentially works is like it's basically all transparent to you, so you don't get to see, you can analyze it and see it, but you don't have to like change the workflow you're using for local computations to do it with a distributed one. And essentially what's happening in the background is when you load the library Dask or use Xarray with chunks, and how do we use that? How do we know we're using Xarray with chunks is we're passing this chunks algorithm, and that basically forces Xarray to open the data set as a data array with a certain chunk architecture. And as we can see over here, it's going to tell us this is a Dask array that gets opened up. And what essentially that means for us is that there's little NumPy arrays that get collected into one Dask array. So the way you can imagine it is essentially those Dask chunks that you see over here are many different, or one or many different NumPy arrays collected together. And effectively, you're doing distributed computations over those NumPy arrays. So it's like a slight layer on top of it. How it does it is, and this is where the lazy computing comes in and why it's important, is essentially it's taking in all the different steps that we're asking it to do. Let's say I'm doing a selection, then I'm doing a sum, then I'm doing an average, then I'm combining everything, and then I'm doing a group by, and so on. It's taking all those tasks, and it's not executing them. It's building up a directed acyclic graph, which is looks something like this, and is then optimizing it for us. So similar to, like, let's say if anybody has experience with databases, you don't pass an SQL query and the database just executes directly. It tries to do predicate optimizations before that. What this is doing is, again, looking at your sort of requests, and it's trying to optimize them, squash them, make them much, much more efficient. And then it's passing them to some scheduler that distributes the workload across many different workloads. So, okay, what this scheduler might look like is it might be something that's, let's say, running on your local machine, which is, let's say it's just doing the distributed algorithms over your CPU. And it's basically putting every thread on your CPU as a separate worker for the distributed algorithm steps. Or it might be something like, let's say, a scheduler on Kubernetes, which essentially this EOX hub environment provides you. And that Kubernetes scheduler is creating a new container as a Dask worker, which is taking on tasks that are orchestrated by the scheduler, effectively computing them and communicating back with the scheduler the results, and taking more tasks and more tasks. And you can see basically the way it's implemented lets you scale it up to, well, not infinity, but very, very much. So how you can basically deploy it yourselves on your own infrastructure. All of it is open source, so you can either very easily deploy it either on your own computer or like on some HPC cluster or some, let's say, cloud. This is essentially just a cloud deployment of that, and it gives you resources to do the compute over it, so you don't have to like basically do anything with the infrastructure. You don't have to worry about anything like, let's say, making sure, well, maintaining it, and so on and so forth. There's also, and the way that it communicates, right, is you have the scheduler, and that's basically, you don't see any of this. What you do see in your Jupyter Notebook is this client. And what the client does is essentially, build the task graph. So that's the component in DAS that builds this graph over here. When it's done building the graph, and you actually want to start computing something, let's say you do .compute or .plot, when it actually has to start computing stuff, it then sends it, only then does it send it to the scheduler, which distributes the work across the workers and then returns you a result. But this is the component essentially that on the front end it's communicating with, and this is what's happening on your Jupyter notebook. No computations are effectively happening here. The only computations that would happen is, like, let's say when you're plotting something, it might do the different computations, and it will then return the data to your front end, and that might crash your, let's say, Jupyter notebook because it's trying to combine and visualize the data on one computer. So just be mindful of visualizations. That's the thing that typically crashes these. Okay, but what have we done here is basically we've created this DAS client, which is a local one. You know, this is how you create essentially a local one. You can create it on your own PC. You don't have to do it in the cloud. Essentially, there's some information about the cluster, there's the scheduler, and there's the workers. So a cluster is essentially just scheduler and workers. What we're going to do is close this one, and because this is just a local one that's basically on the virtual machine of the Jupyter single server instance. And now what we're going to do is essentially connect to something called DAS Gateway. The gateway is a component that essentially connects many different clusters into one environment. So basically we have a deployment of a DAS gateway, and then through the DAS gateway you can deploy and create your own different clusters. So what we're going to do now is try and spin up clusters. So there's different options for the workers. So like you can basically customize the size, the image they're using, the environment, that sort of a thing. And whoops, I actually need to scale it. And basically this is how you create a DAS cluster. And your workflow will typically start off with this. You'll need to create a DAS cluster, scale it. You need to explicitly scale it, by the way. So what this is going to do is, just let's walk through the steps because I think it's going to make it clearer. You first get a connection to a gateway. That gateway is somewhere on the cloud. All the environment variables are getting injected in this command, like basically in the environment, and automatically get injected via the client, so you don't have to like configure anything. It automatically finds it for you. You can set cluster options for like what size your workers should be, what images should they be using, and so on and so forth. We're sort of in a restricted environment now, so we only have a couple of images and so on. There's different ways you can basically set in environments for your workers. And then you need to create a cluster. You can pass in the options that you've selected for the cluster, and that's going to return you a cluster object. And that cluster object is essentially this workers scheduler combination that we showed last time. And then what you need to do explicitly is scale that cluster. What Dask is not going to do for you, you can set it to scale automatically, but you need to also be explicit about that. There's something called adaptive scaling, and that's going to scale based on the workloads you give it. But you need to be very explicit with it. This is essentially going to create workers for you now. So this is going to spawn 2 workers. There's something called the Dask extension, which essentially shows you over here, if you click on the left-hand side on Dask, you'll be able to see essentially a cluster with 2 workers, 2 gigabytes of memory each, well, 2 gigabytes of memory in total, 2 cores, and so on. It's a very small worker, it's a very small image. It's not going to be able to do much. We're going to spawn a bigger one in a second, but basically it's created that. Now, you have that. You need to actually connect with it somehow. You do this through the client, through this client component. To get that, you do cluster.getClient. That talks with the cluster and returns the, well, it doesn't talk anything, just returns you the URLs and everything else for that cluster and how you're able to communicate with it. And then loads a client in the background. This client, you don't really have to touch or do anything. What's going to happen now is any xarray command you run is going to run on the cluster itself. So you won't actually need to explicitly call xarray, use this cluster, do this compute. What's going to happen is your notebook's automatically going to know, xarray is going to automatically know that your compute is going to happen on this cluster using this client that you've just deployed. So notebooks, typically when you see them, will start with some declaration like this where they start or declare or get a client. Okay, what else have we got here is something called the Dask dashboard. And this essentially, you can copy this link over here of the dashboard, enter it over here at the top. And hopefully something's going to happen. There we go. No. Ah, okay. It's just logged me out. Might need to refresh. What essentially Dask exposes is a component, a dashboard component that shows you what's going on in the cluster. It shows you like basically I have 2 workers. I don't have any tasks in progress now, but there is like some information that they're storing some bytes. Basically, that's just to manage the cluster. And I can get some information about what's going on with my workers. And why that's important is because you then will start actually doing compute over it. And I'm just going to quickly copy this. Link over here. There we go. There's something also called the, sorry, I just need to connect to my cluster in a second. So, okay, if you reload your notebooks, and this is important to know if you're ever working with Dask, if you rerun everything, what's going to happen is you're going to create a new cluster and with new workers, which we typically don't want to do because you end up basically rerunning your notebook will create many different clusters. What you typically want to do is like spawn it once and try and like connect with it. So I'll try and connect with it over here now. It's cluster. Well, we need to first get the gateway. And then you need to get the clusters. And that's gateway.list clusters. And that's going to give you all the clusters you have available. And then you can just select the first one. And then what you can do is copy this name. This is just an ID for your cluster. And you can connect with an existing cluster by gateway.connect. Pass in the name of the cluster you want to connect. And let's just get the client of that. And then, well, let's first connect with it. Oops, was the name? Cluster name. There we go. Okay, so we connected with a cluster, and we can get the existing cluster client. So I've just refreshed my notebook. As you can see, it's like a separate cluster running somewhere else, so you can connect with it. Okay, now your cluster, if you spawned it, is going to give you something like this, which is a dashboard. And this dashboard, you can just drag this, copy this link, and paste it over here. It's going to connect this component over here to the left. And this is basically just a much more intuitive view of what's happening in Dask in your Jupyter notebook directly. What you're able to do is essentially get, let's say, well, let's say we visualize the processes progress. Essentially get the different components from the Dask dashboard directly in your notebook, so you get a much nicer view of what's happening. And let's quickly run through and see what Dask is doing in the background. OK, so let's open up the notebook and start doing some compute as well as last time, but this time using our Dask cluster. So we've just opened up the notebook. Now we're going to basically select first from our data set the leaf area index. We're going to resample the data on a yearly basis. So what's that going to do is basically combine all the data and sum it up per year. We're going to basically apply a mask. Well, we're going to apply this mask to it, which is basically the land mask. Why we're doing this is to do a land mask, because we want to get only areas where there's no ocean, where there is some leaf area index, so anything beyond 0. So we're summing it up, then we're applying this mask to avoid anything that has 0 in it. We're selecting a time, and then we're getting some data. What that's going to do in the background, it is going to create for us, the client, this essentially graph of compute. And this is essentially what Dask is going to do for us in a distributed manner when we send it to the scheduler. So let's visualize what happens. let's say we plot it now, and this is what happens in the DAS dashboard. The workers start doing something, they get the data, they start doing compute over it, and the result returns pretty quickly because we don't have a massive compute. And then the plot happens. So important to note is that none of the compute actually happened up to this step. This only did the metadata and built the compute graph, but nothing actually happened. Compute only happens when you force it with either plotting, or you can do dot compute as well to essentially force and start a computation to happen. Okay, and now let's get into a proper workflow with Dask, and I'll get into a bit more detail as well into how it works. Any questions in the meantime? Yeah? Yeah, that's a very good question, and that's typically what you do in a Dask workflow. And basically, that's called persist. So if I scroll over down here just to show you, actually I can search for it. So, okay, I'm calling persist here on some data array, and what's happening there is like the computation up to that point is going to get saved in distributed memory across my different workers. And why you would do that is basically because, let's say you've done a very expensive computation over terabytes of data, much data, and you want to basically not do it again every time you rerun the computation. You persist it across distributed memory, and then every time you basically reference this variable that got persisted, you're going to reference the persisted data in memory rather than basically redoing the compute yourself. So that's one way you can do it. The other way is obviously just store it on a file somewhere if it's like big enough to warrant. But typically what you would do when you're experimenting is you would do the expensive compute, persist it, and then do experimentation, and then remove the data from there, do another round of experimentation, and basically continue that flow until you get to a final result. Okay, so what we're going to do now is essentially run through a quick example of basically analyzing some forest fires using Sentinel-2 imagery and the ceasefire cube we just were working with. So if you open up a Dask cluster, just run this client close step. What that's going to do is essentially kill this client at the bottom for you. Or you can just go into clusters over here on this Dask extension and just kill the cluster directly. Now, if you can go through to the BiDS'25 burnt area example notebook, which is in this burnt area example folder, you should see a notebook called Pangeo on EarthCODE. So let's walk through it step by step. It's basically essentially nothing new from what we were looking at last time. It just combines all the steps together. So let's see like what an example workflow typically would look like in the Pangeo ecosystem, and how you would access EarthCODE data when you're doing your work if you want to explore that. So essentially, for this one, we're going to load a slightly larger cluster. What typically your notebook is going to look like is you're going to have all your imports. If you're using Dask, you're going to spawn the cluster at the start, and you would scale it and connect to it. If you're running this locally later on, you can reuse the same code, by the way, but with a local Dask cluster. So after you load it, you need to load the data. So what we'll do is lazy load the ceasefire data that we previously looked at using these arguments. And again, maybe just to walk through what we're doing is passing a URL. It's looking at that URL. It's only reading the metadata. It's using an engine ZAR in the background, and it's going to use only the chunks. It's using the chunking architecture of whatever is specified in the actual stored data and going through downloading and working only with them. This consolidated argument is something you'll probably see more often with data sets that are sort of analysis ready. What this means is essentially the way ZAR works is that it might be easier to actually show you one if I've got, okay, I don't have it computed, but I'll show you it in a second. But essentially, for each data array or Dask array, you will have, or ZAR array specifically when it's stored on ZAR, you will have like different metadata. What it essentially does is consolidates all that metadata from the different arrays into one central metadata. file. And why that's important is because, again, typically you're going to be working somewhere on a network and you don't want to be fetching metadata a million times because the file is going to be smaller than, and it's going to be less megabytes than the actual network request headers and everything else. So it's very important to like optimize everything to do as little as you can when it comes to fetching new data when you're doing this sort of cloud native compute. So that's what consolidated does. It consolidates the ZAR metadata. Okay, so what we're going to do now is we're going to use this GWIS data variable. And what this essentially is forest fires. Basically, it tells us how much hectares were burned in a particular area. The grid size for this is pretty large, so it's 0.25 degrees. We can see it in the metadata. And it's every 5 or 6 days or 8 days. And essentially, depending on the leap year, and essentially it's, I've calculated to about like 28 times 28 kilometers per pixel. So it's like a very, very large sort of pixel environment. So what we'll do first is subset the data. And what we're going to do is essentially use the polygon that we previously loaded to grab an area of interest. I already have something preloaded that's somewhere in Portugal, North Portugal. So forest fire there at some point. What we're going to do here is first slice the data and get the areas of interest. Now we're doing something a bit different here with slicing that you will see. Why we're doing that is because the indexes of the data are, if you look at it over here, they're regular, and it's up to a certain, like it's 625, 375, whatever. The indexes for our polygon, if you look at it over here, are very much floating, like 32 numbers, floats that have a lot of numbers after the dot. What that will do is it might confuse the way that data is indexed in NumPy. So what we're doing here is instead of relying on slices and the slices API, what we're going to do is directly snap the polygon ends onto our data using the nearest sort of member. And you can try and rerun this directly with just slices without doing this to see what the difference is between the data. Just in the interest of time, I'm going to go forward. So okay, we're building out the latitude, longitudes we want to get. Now we're going to get a B box. And this basically is just this area of interest that we're looking at. We're going to look at let's say we're going to analyze the data from 2018 to 2021. And we can get a time slice by directly just doing slice and like so, and passing it to the selection API for X-array. And then basically what we're going to do is also grab the slice of latitude and longitude that we're interested in. Yeah, so same stuff as last time. Oops, I need to first run this. Okay, it's building some compute in the background. It's not actually like computing it. It's just building the graph for how to compute it. Now, what we want to do is like for this area of interest that we were looking at, what we want to explore is find the time that there was the largest forest fire within that area. So how are we going to do that is we're going to do a sum over, spatial sum over the area and see how many forest fire, how much burned area there was in that area, and do that for each time we have. And then grab the largest time and grab the time where the largest sum is. So this is what ID max does. It directly returns the index of the time. I'm just going to show you the result. But again, we haven't computed it yet, right? So you'll see in a second. What's going to happen, what it's computed so far, though, is this not so distributed sort of process. It's more serial, as we can see. And now, when we do dash compute, it's going to force it to compute this in the background, which we can see over here in the in the dashboard. Just recompute it. Okay, but the computation is happening fairly quickly because of the very small one, so we can't see much. Okay, so we have the date of the largest forest fire here that we computed. It was at 2020, sometime in September. Great. Now we can basically get that data from our data set and see what it looks like. As you can see, like the chunk in the data isn't all that much. It's basically 2 by 2. So there's only 4 essentially data points there. So it's a very brittle data set, this. So because we're looking at a fairly large area as well. And we're plotting it, and we're seeing basically there's one sort of area that's got a larger value than the rest. So we can see one area was burnt more over here. But that doesn't really tell us much. So what we can do is, in the ecosystem, there's a lot of tools for visualizing data, one of them being HVplot. So what we can do is do an interactive plot with this. And essentially what we can pass is, well, the most important things you would be interested in is tiles. So we can easily put a background on the image we're trying to visualize. This is going to download the tiles and do a visualization for us. And then we can set the alpha for the visualization so it's transparent. Okay, and what HVplot also does for us is we have a way of also exploring our data in our data sets. So if this was a time step, I would be able to also step through the different time steps of my data and visualize it very easily. And I can explore the data, see that, okay, we have some values over here of burnt area acres of some acreage and whatever, but this doesn't help too much. We can see that this area over at the top left, the north was burned, but we can't get much. So what we can do is analyze it in a bit more detail and see what was burned in particular and see how it looks like. So, okay, what we're going to use for that is Sentinel-2 imagery at 10 meters resolution. And we're going to use the previous queries we learned in the stack example to get that data. So, okay, what are we doing here first? We're first getting the date of the max fire that we've seen. And we're going to get the week before and the week after and see what areas were burned and how severe the damage was. So just getting the week before, week after. What this looks like is sometime in the beginning of September and then the end of September. Then what we're going to do is fetch the data from Element84's stack endpoint and get the metadata, basically get and load the data. Now, I'm going to run through this and then explain what's happening. So we're doing a couple of things with this query, and I get into detail over here. But essentially, right, somebody asked earlier about cogs and how they work together. What this is, it's doing exactly that. So it's basically, the first thing we're doing here is we're doing a stack search, and that's returning stack metadata. We're not really doing anything with the items. We're searching for a particular collection, which is this one, at a particular time, and we're limiting it to 100 returns for a bounding box that gets intersected in that area with a query that leaves us with a cloud coverage less than 20. And basically, this is going to return only the stack metadata. So this items query is a list of stack items for those trips essentially. But that's not really only our area of interest. It's the satellite image, essentially, of that has an intersect with our area of interest. So it's going to return a much bigger sort of place than what we had in mind. To then use this, what we need to do is directly access it ourselves, or more via the href attributes in the stack items, or better yet, use some library like stack load, which is going to automatically look at the stack items, try and get the href towards the actual data, towards the cogs, download that data, and automatically not download the full data, but only cut the data on the bounding box we're interested in, and then load that into memory for us, reproject it to a resolution and to a projection we're interested in, and then prepare it for usage for us. So essentially, that's what all of this is basically getting done in this one stack load call. So this is why the ecosystem is so powerful, because you can reuse this across, well, basically every cog you see with stack in it. Okay, so we're going to do the same for the period after and before. And we're going to just quickly plot the two areas that we're looking at. Something that's very important in X-array that we didn't cover is that when you're doing like division, multiplication, when you're combining data, or when you're doing sums, and so on, you have to be mindful of where your data has non-values and NAs, because that area will get skipped. So if you do, let's say, a sum on one area and you're trying to compare it with a sum on another area, you better make sure like the areas that you're looking at are the same for what you're trying to figure out. So in this case, like the stack item we're going to load has the same coverage in both instances. But what might happen is if we search through stack, it might return like, let's say, an area that has half of the coverage, and we might calculate, let's say, a sum over only half of the area that we're interested in, and then calculate another half over the other area in a separate query. And then when we're trying to compare those two, we will just fall into error because we will be comparing basically different things, apples and oranges, right? So be mindful of what you're actually loading and what the libraries are doing in the background. Okay, and I'll pass through this a bit quicker since it's already 5, but essentially at this point what we're going to do is calculate a normalized burnt area index, and we're just going to basically do a bit of band maths. So we're going to use the near-infrared and the SWIR bands to calculate this NBR index. We're going to calculate that for our data before the fire and our data after the fire, for a date after the fire. What we're doing here is also normalizing our data, not normalizing, but scaling our data, applying the scaling. And then what we're going to do is persist that data onto our Dask workers. So this in the background will start getting the data, downloading it, and preparing it for use. So this is what persist is going to do. What we're going to calculate then is what's the delta before and after the fire. And then what we're going to do is persist that difference as well. Essentially, by the way, what happens here as well in the background is this does not stop you from continuing the computation. This all happens in the background when you run persist. So you can continue working on your notebook, essentially, running different commands that are going to get scheduled to Dask. OK, so in the end, we get this plot of area that has normalized burned area difference on it. So now we're going to plot this data. And I'm not going to rerun this, so it happens faster. But okay, it's loaded over here. I might actually rerun it. But as we can see, the date before the forest fire, there's not too much burnt areas over here. The date after, we can see there's a highlighted area over here. And this highlighted area is essentially what stands out on the NBR index. What we are going to be doing in the delta is essentially just highlighting this burnt area, right? So what we're going to do next is then classify what areas using a very simple way. As we are going to classify what areas were burned and weren't burned based on what NBR value they got. There's a standard way and standard values that are normalized for this. And for areas that have a delta and a difference between 0.270, that means they have some sort of low severity burn. And what we're going to do next is essentially build a mask for all the area that has a burn for the delta that's bigger than 0.27. And then we're going to plot that. And this is what this gives us. Essentially, this is like the areas that we are assuming are burned after a certain forest fire. And we have a mask now and an idea about how much area was burned. What we can do now is, and what you would typically do in a EO workflow is go out and validate it somehow by doing a field study or like checking actual data. What we'll do is like check it against the ceasefire data we were initially looking at. So what we're going to do here is compute essentially what the area of what the burned area in total was in this image. So how we're doing that is essentially we're assuming each pixel is 10 meters. There's however many pixels here that are burned. Multiply that by multiply that and get the area, and we sum it up and get an assumption of how much was burned in that particular region afterwards. So what we're doing then is also comparing that to, then going in from meters to hectares over here, and then comparing it to the area we supposedly have in our ground truth data, which is the ceasefire cube data from GWIS. And we see there's a small difference over here, but I'm sure if we run it on a larger size, on a larger scale with many more regions, we'll probably get errors because this isn't optimized. We would need to like be more rigorous with these things. Okay, then, and finally, what you can do is plot all those results together, and we can see basically the data sort of aligns. The GWIS data tells us that there is something burned over here in the northwest side of the region, and we can see that our major burns are happening somewhere over here. So visually comparing it, it does make sense. It's like sort of on the same, it's going in the same direction. And then how you actually save the data is, there's a couple of steps, but more importantly is you have something to validate your data, which is called XRLint, and that's going to give you some ideas about what you're missing on your data set, like in terms of attributes and metadata. To make your data essentially fair, you need to include things like attributes to it, which are, you can essentially see over here, or in the, over here in the spatial ref, and it's basically descriptors of what your data is about, and things like CF names and so on and so forth. And then finally, just how saving your data looks like. Essentially, going back to the question about chunking and how you get the original chunks, you would be advised to chunk your data in a sensible way based on how people are going to use it. This is an example. This is probably a very bad way to chunk this data in particular. But essentially, you would need to chunk it in a way where it makes sense for people on how they're going to use it, and then save that data as a ZAR file and share it with the community, which you can look at in this notebook. We can find it over here. Yeah, which you can basically check out in one of the notebooks over here and publish it to EarthCODE later on. I think we're out of time now. So any questions, any suggestions, any ideas, any feedback is more than welcome. Cool. Cheers. All right, thanks everyone for spending the time today. And I'll see you at the pub crawl, collecting the challenges. Come again? What? I have no idea. Somewhere around Riga.